So let's get started. What's happening? Yeah. So let's understand. Let's understand what is dynamic programming. Then we will try to divide the problems on pattern based, and we will solve them. I solve couple. I'll give you few of the exercises. You can do it. So you pick up any dynamic programming. So first of all, dynamic programming is an algorithm. So it's not a data structure. So it can be applied on any data structure. So you can pick up any DP problem, dynamic programming. So it can be divided into multiple subproblems. So a DP problem has multiple subproblems, and we need to always get the optimistic result out of these multiple subproblems. Get optimistic result. So I think we might have heard the same statement in greedy. Even the greedy also same thing. So you have multiple subproblems and will get the optimistic result. But the difference is greedy is always concentrate on current iteration. So with respect to current iteration, what is the optimistic result I could get? For example, you have I 0 to n and I is at index 5. Now with respect to index 5, what is the optimistic result I could get? Even dynamic programming also we follow the same pattern. Uh, you'll get to know when we are solving the problems. Otherwise, it will make confusion. But more or less, greedy also is a kind of DP problem. But all the greedy problems are not dynamic programming. So while solving the problems, you will get to know that. I'll just avoid it. So simple. So you will be given a problem statement, and it has multiple subproblems. Then out of the subproblems, you need to return the optimistic result. Okay, I have a multiple subproblems, fine, and I need to get the optimistic result. So that obviously we already know that you can divide a main problem into possible subproblems through recursion, right? So this is what we did, right? So through recursion, we are able to divide a possible main problem into possible subproblems. That's what we did in backtracking. Now, yes, I can still get the optimistic result. Yes, I can maintain a global variable, and there I can keep the result whatever I want. So I can just return. Then y is dp. So already we know recursion, and we also know how to hold this optimistic result. But what is the point of dp, right? So this is where what's happening? Okay, why it went into this color? Okay, so this is where we get the concept of DP. So for example, I'll give you one standard example, Fibonacci number. Somebody ask you to write the Fibonacci numbers. How does it look like? If you take the Fibonacci numbers, this is how it is, right? So 1, 1, 2, 3, 5, 8, and 13, and so on. So what do you understand here? If you take 2, if you take 2, it is a sum of previous two numbers, right? If I take this number, it is a sum of previous two numbers. If I take this number, which is a sum of previous two numbers, and similarly this number, which is a sum of previous two numbers. So, what did you understand here? For example, I want to find out Fibonacci number of n. If I want to find out Fibonacci number of n, so I can, yeah, so instead of n, let me take it as 5. So every DP defines a function. So every DP problem defines a function. So here I want to generate all the Fibonacci numbers. And you also understand that this is how Fibonacci numbers looks like. And if I want to know the current number, it is a sum of previous two numbers. So if you take up any number which is a sum of previous two numbers. So And we also need to know the base case. So this is my base case. So what do you mean by base case? So in any DP problem, you must and should know what are the base results. Just like in a recursion, right? You know the base case, right? So what do you mean by base case in recursion? It's a least possible valid solution for your algorithm. So that's how it is. Even this case also, when the value is zero, so it means, let's say if Fibonacci numbers 0 to n minus 1. So let's say these are the Fibonacci numbers you want to figure out. So this is at 0, this is at 1, this is a second Fibonacci number, this is third Fibonacci number, and so on. So you also know that if Fibonacci number of 0, which is 1, and Fibonacci number of 1, which is also 1, then I can also know that Fibonacci number of 2, which is equal to Fibonacci number of 0 plus Fibonacci number of 1. Right, so it means, what did you understand here? So if I know the base cases, I can derive the next value from the previous cases. So this is what we need to see. Hope you are following me. So in any DP problem, you must and should know base result. So in this DP problem, so for example, we want to find out a Fibonacci number. The Fibonacci number of 0 and 1, we should know that. So which is 1, 1. Then only you can derive the sub problems. Let's say I want to get the Fibonacci number of 5. So generally what you do, so you can get it, it is a sum of previous numbers too, right? Previous two numbers, right? So it means Fibonacci of n minus 1. So it means n equal to 5 here. So n minus 1 means it becomes 4. Fib of n minus 2. So n equal 5 here. So it is 3. So the sum of these two is going to be the fib of 5. Similarly, if I want to find out fib of 4, so you must divide this into possible subproblems. So fib of 4 can be sum of n minus 1 and n minus 2. So n equal 4 here, 3 or 2. The sum of these two values equal fib of 4. Similarly, if I want to find out fib of 3, then it is going to be fib of 2 and fib of 1. Similarly, fib of 2 is going to be fib of 1 and fib of 0. And you see, these are the base cases. So we already know any DP problem must and should have the base result. So we already know the base cases. We will figure that out. So this is plus, this is also plus. Now similarly, if you closely see, fib of 3 can be divided into fib of 2 and fib of 1, and fib of 1 is divided into fib of 1 and fib of 0. So it means the sum of these two is going to be the zeroth value, and first value is equal to second value, first value, summation is equal to third value. So this is how it is, right? Now it's a traditional Fibonacci problem. If you want to find out a Fibonacci number of 5, how do you do that? So you take up the fib of 5. So this is our function. So we are trying to divide this into possible subproblems. So n minus 1, n minus 2, similarly for everything. And we know the base case, whenever the fib of 1, whenever n equal to 1 or n equal to 0, so we will just return 1, so that it is 1 plus 1. So it is going to be 2, right? So this fib of 2 becomes 2, and fib of 1 value also plus 1. So 2 plus 1, the fib of 3 becomes 3. And again, you see that, again, we say that we need to divide this problem into fib of 1 and fib of 0. So this is also 1 plus 1, so which is going to be 2. Now 3 plus 2, which is going to be 5. Similarly, in this case also 1 plus 1, so which is going to be 2. And this is also plus 1, so 2 plus 1, which is going to be 3. And 5 plus 3, so which is going to be 8. So it means we figure out a Fibonacci number of 5. Now, what did you understand here? If you closely see, we divide a main problem into possible subproblems through recursion. And we also know that in a recursion, a base case is very important. When the n equals 0 or 1, so we are just returning 1. So we are just giving sum of those two values to the previous caller. So that's how it is working. It's a pure recursion and finding out the optimistic result. But the only problem you could see here is we are having duplicate overlapping subproblems. What are those? Let's see here. Let's see here. So here we solved already fib of 2. And again, we are trying to solve fib of 2 here. and again we are trying to solve fib of 2 here. So it means we are trying to let me highlight this. So we have solved fib of 2 here. Again, we try to solve here and we try to solve here. And similarly, do you have, yeah, we have solved fib of 3 here. Again, we try to solve here. So what are we trying to do here? If you closely see, what is the time complexity of this problem? What is the time complexity? If you don't apply dynamic program, can you tell me what is the time complexity? Can you please tell me? What are we doing here? For each subproblem, we are trying to divide into how many? How many subproblems? For each problem can be divided into how many subproblems here? Two, right? So 5 is divided into two subproblems. It means there are n elements, right? There are n elements, and each problem is divided into two subproblems, so which is going to be 2 power n. But can you optimize it? So why it is happening like this way? Because we are not at all. Why it is happening? Why? Because we are trying to divide the same problem into possible subproblems, and if you closely see here, uh, we are having overlapping subproblems. These all are the overlapping subproblems. We are trying to solve those problems again and again. That's where the concept of dynamic programming uh, comes up. So let's say here. So that's where the concept of dynamic programming triggers here. So what DP says, uh, cache the subproblem results, then reuse them. That's it. This is what DP says. So you can divide main problem into possible subproblems. Whenever you are dividing the possible subproblems, solve the subproblem only once. So what do you mean by? So it means what? Solve it only once, only first time, and reuse it. Reuse the result. So this is what it is. So this is what it's trying to say. Now, if you closely see, let me try the recursion problem again. So we have f of 5, so which is divided into f of f of 4 and f of 2. Okay, nice. Again, f of 4 is divided into, sorry, f of 3. So f of 4 is divided into f of 3 and f of 2, and this is divided into f of 2 and f of 1, and f of 2 is divided into f of 1 and f of 0, right? So you know that this is 1 and this is also 1, so 1 plus 1, so which is 2, and this is 1, so 2 plus 1, which is 3. So first what we try to do is we try to represent, so we need to represent this in the form of a cache. So first we need to represent this form of in the form of a cache. So what do you mean by cache? You can pick up any data structure. Let me go here. So yeah. So what we do whenever we are trying to solve any DP problem, so first we try to solve through recursion. So that's the try to call we try to solve that problem into recursion. If you are solving a DP problem through recursion, we call it as a top-down approach. What do you mean by top-down? So we are starting from top number, right? So we want to find the number of we are from where you are trying to derive the subproblem. That is what defines whether you are going with top down or bottom up. So this is top down because we are starting the value from the top value. So main problem, so which is 5. So then we are trying to divide into possible sub problems. Then we try to solve them. So what we are trying to do is this is a traditional DP problem. Let's assume I want to cache the results. So cache the sub problem results. So this is what talking about the state of your dynamic programming problem. So what do you mean by state here? So here I want to generate, I want to find out Fibonacci number of 5, right? So how many possible subproblems I can derive it? in worst case? How many possible subproblems I can derive this? I want to find out Fibonacci number of 5. How many possible unique subproblems I can get? Can you please tell me? You can say 5, right? So yeah, so 5, right? So it means you can get unique subproblems of 5, right? It means you need to represent that unique subproblem results. You need to represent that unique subproblem results in the form of a data structure which will cache that result. So that data structure can be anything. So what I will do, I will take a simple integer array. So I can take it as a DP, which is equal to a new integer array of the size, right? I want to find out the fifth problem, right? So generally, if I take 5, so it is 0 to n minus 1, so that it means the value of index number is defining the sub problem here. So if I take 5, so 0 to n minus 1 means it is going to be 0 to 4 only. But I want to find out the subproblem of 5, so that I will take n plus 1, so that this is going to be new integer of 6. So first of all, what I will do, I will just this is my DP. So what I'll do, I'll just take my DP array. Okay, nice. So this is my cache result. So and I just divide this into 6. So 0, 1, 2, 3, 4, 5. So initially, everything will be filled with -1. It means you didn't solve it. You didn't solve that problem. Everything you filled with -1. Then what you did, base result, right? So what I said, so in DP problem, one is state. This is called state. So one is state. First, you need to know what is the what is your state of sub problem and how do you want to represent. So even this n is your state. So I'm representing that in the form of a data structure called array, and I'm just whatever problems which are to be solved, I just replaced with -1, and I know the base result. When n equals 0 or n equal to 1, the value is equal to 1. So -1 means it is not solved. That's it. Second thing is, second thing is we need to identify. So first is state, second is base result. Okay, so we know the base result. So the base result is when n equals 0 or n equal to 1, then return 1. Okay, so this is base result. And what is the third one? Third one is recurrence relation. So recurrence relation. So what do you mean by recurrence relation? For example, if I want to find out a Fibonacci number of n, and how do you find out? If I am able to solve n minus 1, if I want to find out Fibonacci number of n, let's say f of n, and I can derive this if I solve f of n minus 1 plus f of n minus 2. So it's a sum of these two subproblem results. This is what we call it as recurrence relation. So in any DP problem, you need to define these three pointers. So first state, then what is the base result, and what is the recurrence relation. The state is talking about the cache result and what is your method is going to take. So the method is going to take the two parameters, the n and the state. State means this cache object, and the base result and the recurrence relation. Now let's solve here. We try to divide this main problem into possible subproblems. Okay, so let me move here. So first f of 5. Is f of 5 solved? No, it's not solved. So let's divide into possible subproblems 4 and 3. Is f first let's try to solve f of 4. Is f of 4 is solved? No, it is not solved because value is -1. Let's divide into possible subproblems f of 3 and f of 2. Is f of Let's solve this one. Is f of 3 is solved? No, it is not solved. So let's move on. So it is divided into f of 2 and f of 1. So let's say is f of 2 is solved? No, it is not solved. So let's divide it into f of 1 and f of 0. Now you know that when you reach to the base case, this is your base case, right? So f of 1 and f of 0 is your base case. So when it is base case, definitely you can return this value returns 1. This is also returned. The plus is going to be the summation of these two is going to be 2. So whenever you get a result, right, whenever you get a result, update that result into the memory. So this is your DP array, right? So it means you solved DP problem of 2. So just store that result into this DP array. So the value will be updated to 2 now. Now let's go further. Let's go further. So f of 3, now you know that, so f of 2 return value 2, f of 1 returns value 1. So 2 plus 3, which is going to be 3 now. So now let's go and update that dp of 3, right? So dp of 3 is going to be represented as value 3. Now it means you are able to solve from f of 4, you are able to derive this part. So from f of 4, you are able to derive this part. Let's move on to other part. So let's move on to other part. So whenever you are moving here, right? Let's say is f of 2. It means n equal to is already solved. Yes, it is already solved. So that you don't need to read, you don't need to you don't need to solve it again. So that which is already been solved. So that you can blindly return that result. So you can blindly return that result. So the result is 2. So 3 plus 2, which is going to be 5. So now go to f of 4 and store the value as 5. Now again, it means if you closely see, with f of 5, you first solved f of 4, then you are trying to solve f of 3. Okay, so you are trying to solve f of 3. Now let's move on. Is f of 3 already solved? Yes, it is already solved. So that don't solve it again, don't solve it again. So what you can do, as it is already been solved, take that result and return. That's it. How do you know that if the problem is solved or not? So just if the value is -1, it is not solved. Other than -1 means which is already solved. So you just get that result, take that result, and finally return that result. F of 5 will have value 8. So it means the last index is having the total weight, total value. So you just return it. Did you understand? Did you understand here, please? So what are we trying to do here? What are we trying to do here? Whatever overlapping subproblems, right? Earlier, this is overlapping subproblem, right? In earlier diagram, all the overlapping subproblems we are trying to solve it again and again, right? Yeah, so all the if I solve here and again I'm trying to solve again and again. So these are overlapping subproblems. So we are trying to, so if I solve here, so I didn't know to solve here and here. So that, but again I'm trying to solve it. So this is what, which is what making my time complexity is too high. So how can you define the time complexity of this problem, right? How can you define the time complexity of this problem? Can you tell me what is the time complexity here? Why it is order of n? Here also, that's correct. That's correct. But if you closely see f of 5, which is divided into f of 4 and f of 3, and f of 4 is also divided into 3 into 2, and 3 is divided into 3 is divided into 2 into 1, and this is also divided into 1 into 0. So it means if you have n problems, if you have n problems, and each problem is divided into two subproblems, correct? Yes or no? Each subproblem is divided into two subproblems. I know big O of n is correct, that is correct, but I want you to, uh, yeah, I want you to be avoid the confusion in future. You are dividing n into two subproblems. Why it is not 2 power n? This is also same case, right? This is also same thing, but here also we divided each n is divided into two subproblems, but it becomes 2 power n. But in this case, why it is not 2 power n? And what is the precise time complexity? If you say precise, what is the precise subproblem? So in this case, each subproblem can be divided into possible subproblems. It means if there are n subproblems, we are divided into two subproblems, and we are solving subproblem only once. It is going to be into 2. It's not 2 power n, so that it is 2n, and you can say it as n. Correct? Correct, nobody? In other case, it's not like that. So we are trying to resolve again and again so that how many times it occurs, we try to increase that, what do you say, that recursion tree. That's why it becomes 2 power n. But in this case, it is into 2. So we are trying to solve only once. And for each subproblem, you will get two. For each problem, you will get two subproblems. Into 2s, it is 2n, but still it is n. Time complexity is clear, right? So what is the space complexity here? So we have two things. So yeah, so we have stack frame and the DP array. So what is the size of the stack frame, max size of the stack frame? N only, right? So this is what, for example, if you see in this day, in this, so this is the highest stack frame you see, right? So which is equivalent to size of N. The stack frame size is equal to big O of N. Sorry. So what is the DP array? So if you closely see, the DP array is going to be same. So N plus 1, so which is also N. So that's how you can improve the time complexity with dynamic programming. So if you solve this problem through recursion, we call it as memoization. So we call it as memoization. So this is what we did, memoization. So in DP, there are two techniques. One is memoization, other is tabulation. So the best way to solve the tabulation is first you should come up with memoization. So first you should come up with the base case. First you should come up with the pure recursive solution. Then find out what are the possible subproblems. Then convert that into memoization. Then convert the memoization into tabulation. Okay, convert the memoization into tabulation. That's it. So, but if you try to solve tabulation, right, it is like you are by hearting the DP problem. You cannot, it's very hard to come up with tabulation solution. But for the first problem, let me explain about it, how tabulation should be. Tabulation is always be bottom up. The bottom up means you start from subproblem 1 to n. So, but in memoization, we solve n to 0, right? But in this case, it is 0 to n. So that's how you do it. So in a bottom up, so the simplest way, first let me write this code so that we can convert that code into uh, tabulation. So let me do this. Yeah, it's, so we need to just return the Fibonacci number. So Fibonacci number of 2. Okay. So he is saying, so he is also giving that in this use case, this problem we discussed from 0, zeroth value is 1, right? But in this case, he is saying fib of 0 equals 0, fib of 1 equal to 1. He is also giving the recurrence relationship n equal to n minus 1 and n minus 2. So we need to return what is the value of fib of 2. If 0 is 0, 1 is 1, so then fib of 2 equal to 0 plus 1, which is 1. So our example and this example, slight difference, but don't worry about it. So if you come up with purely brute force, right? So what do you do? So if n is equal to 0, you only given the base cases, return 0. If n is equal to 1, then return 1. Okay, so these are the base cases. Otherwise, you can return fib of n minus 1 plus fib of n minus 2. That's it. So this is the simple recursive problem, but definitely if I submit this, it will leads to 2 power n time complexity. It will lead to time limit. So I want to yeah, so I want to improve this. So that what should I do? Simply I am going to define my dynamic. I am going to, this is my pure DP problem. So Now I just try to find out a Fibonacci with memoization. So I need to define the state. So one is I need a n. Another one is I need to store the subproblem results. That subproblem results can be represented as dp. Now I know that if my dp of given n, if it is not equal to -1, if it is not equal to -1, I will just simply return that value. That's it. So we already discussed about it. So if it is not equal to -1, we will just return it. Otherwise, what is our job now? Current dp of n, which is going to be the sum of fib of n minus 1 comma dp plus fib of n minus 2 comma dp. So we are just, this is what, right? So this is what defining the state. And we also need to define the base result. I'll copy here. Base results I can represent here. And this is my recurrence relation. So once you get the dp of n, you simply return dp. That's it. So now again, what should I do? So I need to define the state. So integer dp. So new integer of n plus 1, because I need to find out n, right? So that n plus 1. So dp of first, what I'll do, I'll just fill all the values with -1. Okay. Now I know the base results. So what is the base result? dp of 0 is 0 according to the problem statement. And dp of 1 is equal to 1. Then finally, what is our job? Simply we call this fib by passing n and dp. That's it. So it can does the job. dp of n, right? So it's not dp, so it's a dp of n. So whatever subproblem you are solving, just return that subproblem result. Hope you are following me. As we already discussed on backtracking, lot of things. I am not explaining the flow again. What is saying? Okay. So what is the problem here, right? So it's a base case issue, right? It's a base case issue. If you closely see, so is saying that the size of the given input can be 0 to 30. So this is why, right? So if the n equals 0, if you are trying to solve it 1, then obviously which is returning out of bounds exception. So you can say if n equal to 0, if n equal to 1, if you closely see, this is what it is trying to say. N value he given 0. Okay, so if n equals 0, you can simply return 0. Uh, if n equal to 1, you can simply return 1. So this is how, for 1 it will work, but when n comes 0, definitely it will cause issue. So that's it. Let me submit. So it's a pure simple code. Hope you all understood, right? Any questions on it? Any questions? Okay. Kalyan, Akash, Banu. Okay. You can give a thumbs up. So whenever I say you understood, just give a thumbs up so that we can move further. So this is pure memoization problem. So what are the things we are doing? So we are representing the state of a deep problem, and we are also defining what are the base cases. This is base case, and we are also defining what is the recurrence relationship. So this is recurrence relationship. So if you want to convert this into tabulation, so in tabulation we are just doing bottom up. So we are just doing bottom up. So simple, what you should do. Okay. If I make it more clear, right? In case if I want to make it more clear, so can I do like this? dp of n minus 1, which is equal to this, and dp of n minus 2, which is equal to this. Can I do like this? Is it fine? Is that correct? Is that correct, buddy? So if I run it, still it will work, right? Now, so now you understood what is the recurrence relationship and you understood what are the base cases. That's it. You can easily write, you can easily write a simple iterative approach. So let's see, let me park this aside. Uh, yeah, so let me park this. I don't want you to derive that tabulation again and again. So this is a standard format. So what you should do, it's very tough to come up with a tabulation solution. That's why you should train your brain such a way that from the recursive part, I can derive the tabulation solution. So one thing for sure, so if the base case will remain same, so fine. So this is my base case. And my cache also will remain same because the state of an object will remain same. And I know that this is my base results, so I don't need to worry about it. So this is my base results. If more than that, I need to solve the subproblem. So 0, 1, so these are my base results. So simple. If you closely see, I copy the same state, okay, and I copy the same base case. Now it's a bottom approach, right? In a top down, what we did, so we are trying to solve from n to bottom, right? So we went till n to 0. But in this case, we are trying to start from the base problem. So we already know the subproblems of 0 and 1. So we need to know where to start. So I need to start uh, some, what do you call, I index, let's say index. So I'm starting from 2 and which is moving towards n. Okay, so which is moving towards n and index plus plus. Okay, perfect. So I just started from 2 and which is moving towards n. Perfect. So because it's a bottom up, so it's a iterative approach. We can call it as tabulation is a bottom up. We can also call it as iterative approach. So the main problem with bottom up is we should know order of the subproblem. So in which order we should solve the subproblem. But in case of top down, you don't need to know anything about it. So you just need to the only problem we get to solve through the only problem. Yeah, what's happening? Okay, is it closed? Yeah, sorry. So the only problem we get through bottom up is generally why we can't able to derive bottom up solution directly is in bottom up we need to know order of solution in which order the program should be executed. But in case of top down, we don't need to know anything. We just need to know what are the sub problems we need to divide. That's it. So once we derive it with this recurrence relation, it will auto solve. That's why what you should do, take that same problem and try to convert that into bottom up solution. So then bottom up, so we need to zero after base case, what is the value you want to solve? Just take that value. Then you need to know the base case. So you already know the base case. Now in simply what you can see, what you can do, and dp of current value, dp of current value. If you closely see whatever recurrence relation you solved here, right? Take that recurrence relation and paste it here. So paste it here, but here earlier we started from n, right? It means it's a top down, but instead of n, you just replace with index. That's it. Don't think too much. And finally, you can return dp of n. Understood, buddy? Understood. So what we did, so we took the same problem, right? So we took the same problem. So we define the state and we define the base cases and we know where to start. That's it. Recurrence relation you must copy from the recursive solution or memoization solution. Don't come up with your own thought. It will not come. For this simple problem, you will get it. But in future, whatever problems you are trying to solve, right, it's very hard to find a solution for tabulation without a recursive approach. And what is the time complexity here? What is the time complexity here? Order of n, right? And the space also same. The generally in any TP problem, recursive solutions are recursive solutions are uh, easier to solve, but definitely with respect to performance, right? Definitely it's not optimal. So that's why because the DP problems, right? It is going to take a lot of call stack, right? So call stack size generally hardly in the lead code problems hardly you will see 10 power 5 input or 10 power 10 whatever it is. So that generally our systems are so optimized that it can able to handle even the worst case also it can able to handle 10K or 1 lakh stack frames. But when the input size is really huge, for example, you want to find out a shortest path from US to India, then you need to find out all possible ways. Definitely, it can reach lot of stack frames. So generally, what I'm trying to say is, with respect to execution, right? The stack frames definitely take consume lot of time when the input is too large. But when you try to solve in lead code, right, most of the recursive problems runs faster than tabulation problems. But in real world, it is quite different. But coming up with tabulation solution is really difficult. You cannot get it unless you are not clear about the recursive solution. So going forward, what we do first we solve recursive solution, then we convert into memoization, then we convert that into tabulation. So while converting into tabulation, right, we don't need to put much brain. We just take the memoization approach and we will try to convert. And if you have time, then try to derive that tabulation solution by taking the table and all. But that's not required. Okay. But now can we improve this problem furthermore? Can we improve this problem furthermore? Yeah. Why? Because to solve the current problem, we need to know only previous two problem results, right? Yes or no? To solve the current problem, we need to know only previous two problem results. We need not to know complete result, right? Everyone, please. Correct? Thumbs up. It's like begging for your thumbs up. Okay, so I simply need to know previous two problem results so that I don't need to worry about considering this DP array. So I can take N1, which is 0, and N2, which is 1. Then what I will do, I'll take temp, so which is going to be N1 plus N2. Okay, which is going to be N1 plus N2. Now this is the tricky part, right? Now, if you closely see earlier, we have 0, 1 as N1. Now my temp is going to hold one more value, so which is 1, right? Now, if you closely see, these are going to be my latest two problems, right? These are going to be my latest two problems. Earlier, this is N1. If you closely see, this is N1 and this is N2 and this is my temp. This is my temp. Now, now if you understand for the next problem, right? For the next problem, these are going to be my latest subproblems. So that what I should do, so in this case, which one is going to be N1, which one is going to be N2, buddy? For the next problem, perfect. That's it. So what you should do, your N1 will be replacing N2 and your N2 is going to be temp. And where the final result will store, will hold, where the final result will present, where the final value will be present. But temp is not accessible here, right? If I write temp, it's not accessible, right? One solution, yeah, temp is already copied into N2, na? So you can simply return N2, right? That's it. So now what is the space complexity here? Just I unnecessarily submitted it. Yeah. So it's order of one, right? So we are not taking any additional space. So that's how you derive it. So that is how we should solve the DP problems. So this is our structure now. Okay, so we have 10 minutes, right? So we can solve one more problem. So first, what are the things to remember? First one is understand base case. So then uh, understand the state of subproblem, so that you can derive it. So you can derive it possible subproblems. Then find recurrence relationship. After these 3 points only, you should come up with recursive solution. Then first you do recursive solution, then convert to memoization, then convert this to tabulation. Okay, don't write table and trying to do that. So it's very tough. Yeah, yeah, Ajay, you are saying something. Then yeah, yeah, 1 minute. Yeah, I'll tell that. So then what is the fourth step? Memory optimization. So generally you will get four solutions. So these are the four solutions. So you have to give, possibly you have to, if memory optimization is required, you can do this, otherwise you can do it. The state of this subproblem, right? This is your state, right? These three variables are your state, right? N1, N2, and temp. That is your, actually, if you closely see, N1, N2 is your state. And this is your recurrence relation. And you are trying to divide it. Okay. And this is also changing, right? It is also changing, right? So if it is not changed, you can say it as a base case. It is changed. State of subproblem. Yeah, yeah. State of subproblem it is. State of subproblem. So if you closely see, when we try to solve it, right? So what we are trying to pass, n comma dp, right? So this is state of subproblem. So what do you want to, what is the current state of the subproblem? So n equal to 5. dp is initially for 0 and 1 it is solved. For remaining it is -1. So that while solving the subproblem, you will get that, okay, current is solved or not. If it is solved, then you return. Otherwise, you try to solve it. Get it? Okay. Now, so with this understanding, I think you can solve. I will solve this climbing stairs, but you solve the other problem. Or try solving this n Fibonacci series today itself with the same understanding, so that it will be easy for you. We have 740, but it doesn't take much time. So as we already know the concept. So what he's trying to say is, let's see the problem statement. So you are climbing a staircase. It can take n steps to reach the top. Each time you can either climb one or two steps. How many distinct ways to reach the top, to reach to the top? So this is what he is trying to say. So this is a typical, first let's understand what it is, and let me explain the problem statement here. Is it fine if I discuss now? I think it won't take less than 10 minutes. Fine, right? Okay. So what is trying to say? 70 climbing stairs, right? So what is trying to say? This is your top of the stair. So this is your top of the staircase. How to write the steps? Okay. Step one, step two, step three, and this is assume you have four. So that is your top of the stair. So what he's trying to say, so for simplicity's sake, let me avoid. So this is becoming 3. So is giving n equal to 3. What he's trying to say, you can reach top of the stair, it means to the nth step, either either, for example, if you want to reach step 3, you can reach from step 1 or step 2. From previous two steps you can reach here. So what he's trying to say, for example, this is the top of the stair, this is the top of the stair. So if I want to reach here, if I want to reach here, how do I, at a time you can take one step or two steps. So he's saying it's not like that. So he's saying each time, each time either you can climb one step or two steps. You want to find out how many distinct ways you can climb to the top. So this is what the problem statement says. Let's say n equal to 3 given, n equal 3 given. So let's see the possible ways. Let's see the possible ways. Then we will try to see how can this be solved. Okay, so you have this, how this is how it is, right? So it is 1, it is step 2, and this is 3. What is the possible way? Okay, if I take one step at a time, so first I will reach here. Then from here I can take one step. So that one way is, this is one way. I can reach one distinct way. Let's see one more way. Can I get one more way? So uh, let's say you have step 1, step 2, and this is top. So what I'll do, I will directly take two steps. Okay, so from bottom I can directly take two steps, because either you can jump one step or two step at a time, so that I can directly take two steps, and from here I can reach here. So that this is going to be one answer. So that what he's trying to say, find out possible distinct ways to reach nth step, or nth to reach to the top, so which is represented by n. So this is one way, and this is another way. Do you see any? So this is another way, so that obviously the sum of these two is going to be 2. So he is just expecting the answer as 2. So if you closely see, for what he's trying to say, n equal to 3. Okay, yeah, there is one more way also. Actually, I given diagram wrong. Let me, okay, so this is 1, this is 2, and we have 3. Okay, so you are bottom now. So actually we are bottom now. So first what I do, I'll take step 1 here, then step 1 here, then step 1 here. So I reached to the top. So this is one way. I got it one way. Let's go furthermore. Again, this is 1, 2, and 3. So one way is, I can take just step 1 here. Then from here, I'll take two steps. So I can reach the top. Okay, so this is one way. And find out one more way. So 1, 2, 3. So from here, I can take step 2. So it means I can take either one step or two steps at a time. So from here, I can reach here. So this is 3. So we found total possible ways are 3. So we just need to return 3. Problem statement is clear. You can climb either one or two step at a time. So this is the critical point. Now, now first let's understand, this is your problem, right? So you can climb either one step or two step at a time. First, let's understand what is a base case. What do you mean by base case? How do you define a base case here? Perfect. Yeah. So it means that's how you need to think about same Fibonacci. Just a minute. Yeah. So you need to come up with same thing, right? So base case means what are the base problems? Okay. What if n equal to 1? What if n equal to 1? So n equal to 1 means what, man? You will have only one top, right? So this is how it is. So if n equal to 1, what is the result you will return? The result will be what? 1. What if n equal to 2? It means you have 2, something like this. You have 1 and 2. So what is the result you could return? Right? So 1 1 or 2 2, right? So definitely it is the result is equal to 2. So it means when n equal to, so this is how it could be, right? So 1 2. So you take one step here and one step here, and one way is 1 2. So you can directly take steps here. So now you understood the base case, right? So how did you know that I should know n1 and n2 only the base cases? How did you know that n1 n equal to 1 or n equal to are only the base cases? From the problem statement. For example, he said that you can climb either one step or two step at a time. But if we say that I can climb one step, two step, or three steps at a time, right? Then you should define a base case for three, n equal 3 also. Understood? So the base problems we need to define from the problem statement. So in the problem statement, he said that you can climb either one step or two step at a time. Okay, fine. Before getting into the memoization, memoization, when you get into the memoization, you need a DP state. But if you don't get into memoization, where is that other one? Okay, here. Okay, so you don't need memoization. Before getting to memoization, so let's go into recursive solution. So recursive solution, so we just need one is base case. So when n equal to 1, so we return 1. Okay, and when n equal to, and we return 2. Okay, nice. So fine. This is base case is done. And for recursive solution, right, you don't need to know, we don't cache the sub problem result, so that we don't have cache object. But what is the recurrence relation here? Please tell me what is the recurrence relation here. Let's say sum of these two means what? For example, I want to find out recurrence relation of, if you see staircase of n. How do you represent in the form of n? So it's not easy to write a recurrence relationship directly. So that is for sure. So what you should do now, you know the base case, right? You know the base case. Let's say n equal to 3. Okay, so n equal to 3. So what you do? Let me take a staircase of 3. I can reach 3 either from 1, either if I take one step from second step, I can reach stair 3. If I take two steps from first step, so I can reach 3. So S of 2 and S of 1. Similarly, S of 2, I want to reach staircase 2, right? So second, if I take one step from first step, I can reach 2. If I take two steps from the bottom, I can still reach 2. Get it right? Get it, nobody? So, uh, okay, so if I take two steps from the bottom, still I can reach 2. Uh, Now you have divided it, right? So now you know what is the value of you know what is the value of 1. What is the value of 1? What is the value of 1, man? Staircase 1, base result, right? So base result, which is 1. And what is the value of 0? Yeah, this is also more important, man. When n equals 0, what is the value you need to return? Mm, yeah, so why we came to here? This is a more confusing thing is why we came to here. These are the base problems now, buddy. These are the base problems or not? If you derive subsequently, right, then that will leads to the problem. So what I'll do, We should not come there. So whenever there is a base problem, we should stop. So that is one critical part in DP. So let's see. Okay. Further, right? We already have, right? So n equal 3, it means you can divide it into, first let me solve it, then we can a subproblem of staircase of 3, so which is 2 and which is 1. And we know the base cases. For 2 it is 2, for 1 which is equal to 1. So for 3 it is going to be 3. So sum of these two values is going to be staircase of 3 now. Yes or nobody? You can reach from second step, or you can reach from first step. So number of distinct ways of second step, number of distinct ways of first step. The sum of these two values is going to be the staircase of 3. Similarly, let me take for better clarity sake. So let's say n equal to 5. And we know that when n equal to 1, we need to return 1. Return 1. So when n equal to, we need to return 2. So we know the base cases. So now let's derive it. So staircase of 5, you can get from the second step. If you get from second step, which is s of 3, you can get from the, it means from 3 you can take 2 steps, or from 4 you can take 1 step. And similarly, S of 3 means what? You can take from 2, from 1 you can take 2 steps, from 2 you can take 1 step, so that you can get it. And similarly, this one, S of 3, right? So S of 4 means from 2 you can take 2 steps, from 1 you can take 1 step. Okay. S of 3. Now we know the result of this one, right? 1 is 1 and 2 is also 2. So you can return 3 here, right? So you get 3 here. Then again, I'm not redefining the same thing. So you already know f of 2 equal to, and you already know f of 3 equal to 3. So 3, so 2 plus 3, which is going to be 5. And these two summation, 3 plus 5, which is going to be 8. So you just need to return 8 here, S of 5. Now tell me the recurrence relation. What is the recurrence relation here? Yeah, you should tell in the form of function. So staircase of n equal to n minus 2 plus n minus 1. That's it. So once you get the recurrence relation, that's it. So we are done with recursive solution. Then we will convert this into tabulation. Sorry, memoization. So what are we trying to do? So I have given a memoization diagram here, but you know, right? So if you want to convert this into memoization, what you should do? Do you want me to write the complete recursion tree, or it's fine? Everyone is comfortable, right? So ideally, this is how it should be, right? If it is a pure recursion program, so this is how it should be, right? So S of 1, S of 2 base cases. S of 3 is even give to 2, 1. So this is how it should be. So if you closely see, this is 1 plus 2, 3. This is also 1 plus 2, 3. And this is 2. 2 plus 1 will be 5. So 3 plus 5, which is going to be 8. So what is happening here? We are trying to divide, we are trying to solve. So we solved S of 3 here. Again, we are trying to solve here. So we need to avoid that. So how do you avoid that? So we also know the uh, recurrence relation. What's the time now? Okay. So recurrence relation. So S of n equal to S of n minus 1 plus S of n minus 2. Okay. Then if you want to solve with memoization, what you should do, buddy? If you want to solve with memoization, what should you do? So what we did here, if you closely see, we figure out a base case, we understood the sub problems, and we find out a recursive solution, recurrence relationship. Then we given a recursive solution. Then we need to convert this into memoization. So to convert this into memoization, we need to understand what are the sub problems which are repeating, right? So now how do you come up with the memoization? Tell me. So what should I do now? In memoization, first of all, I need to represent the subproblem state, right? Yes or nobody? So how many subproblems I can get here? how many subproblems, unique subproblems I can get? Unique subproblems. If you closely see how many unique subproblems you are, how do you know the uniqueness based on the n value only, na? Yes or no, bro? So these all are unique. One, two, three, four, five. So these are all the unique. So other things I don't need to solve it again. So it means I can get at least n unique subproblems. Correct? Correct, na? Am I confusing you or is it fine? Akash, Vanu. So first, this is clear, right? This part is clear, right? This part is clear. And in this part, we are just returning we just written a plain recursive solution. So in this case, we understand that S of 3 solved more than once. S of 3 solved more than once. We want to avoid that. To avoid that, we are going with the memoization. To go with the memoization, we need to know the subproblem state. How do you say these two subproblems are same? How are you saying these two subproblems are same? Akash? How do you know that we are deriving twice? Based on which value you are trying to say these two problems are duplicate? Based on value 3 only, na? So this value 3 is nothing but n only, na? N equal 3 only, na? Yes or no? N equal 3 only, na? It means what? If you closely see, n equal to 1, 2, 3, 4, 5. So it means there are only 5 unique subproblems. So all other are duplicate subproblems. So that's why you should come up with a cache which is going to represent our DP, and my DP size which is exactly equivalent to n plus 1. So if n equal to 5, so that you should represent it as 6. Okay. Now you should save the base results dp of 1 which is equal to 1 and dp of 2 which is equal to. So if you closely see, this is how it is: 0, 1, 2, 3, 4, and 5. We don't consider this zeroth step. Of course, we don't require it. So it is 1, it is 2, remaining all are minus 1. Now what you do? Now you are trying to staircase of 5, which can be divided into staircase of 4, staircase of 3, and which can be divided into staircase of 2 and staircase of 3. And yeah, so this 3 is divided into staircase of n minus 2 means 1 and n minus 2 means 2. So you know the base. Now this is how it ideally it should flow. So let's move on. So first you start from staircase of 5. First we try to divide into n minus 1 and n minus 2. Let me maintain the same order: n minus 1 and n minus 2. So it becomes, let me swap it. Okay. Yeah. So in the left side we are making n minus 1, in right side we are making n minus 2. That's how it is. So it is n equal 4 here. So that's how we try to do it. Okay. So let's see here. First we start from n equal 5 and n minus 1 we try to do. Yeah, n equal 5. Is it solved? No, because it is minus 1. It goes to n equal 4. Is it solved? No, it is not solved. So it goes here. N equal 3. Is it solved? No, it's solved. It's not solved. Then it goes to n minus 1. So which is becoming, let me change it. So this is 2 and this is 1. So n minus 1. So n minus 1 means here, if you closely see here, n equal 2, right? But 2 is already solved because we already stored the base result, which is 2. So if the problem is already solved, don't derive it again. So just return 2. Okay, we return 2 here. Perfect. So we return 2. And for once we return 2 here, then it will look for n minus 2 subproblem. So which is 2, right? So which is 1. So for 1, which is already solved, so that you can return 1 here. So the sum of these two values is going to be this n equal 3, right? So third subproblem, which is going to be 3. So you get 3 here. 2 plus 1 is 3. So what you do, you update that value into dp of 3 is going to be 3. It means for s of 4, if you closely see, for s of 4, n minus 1 subproblem we solved. Let's move on to n minus 2. So n minus 2, which is 2, right? So for 2, you already solved it, so that you can simply return 2 here. So the 3 plus 2, which is going to be 5. So, okay, so for s of 5, s of 4, which was given 5. Now, if you closely see, so we have already solved n minus 1 subproblem for n. Let's move on to n minus 2. So when you move on to n minus 2, it is n equal 3. So 3 is already solved, right? 3 is already solved, so that don't solve it again. Just return that value 3 here. Then the sum of these two values, 5 plus 3, which is going to be 8. Okay. S of 4, we didn't update here, and s of 5, it becomes 8. That's it. So we'll just return 8. And finally, where the result will be present, so dp of n will hold the value 8. So we just return that. Clear, right? Clear na? Mm, yes. That's why it's a Fibonacci pattern. But if you look at the problem statement, you don't feel like that. So when you write the recursive diagram, right, then you will understand that it's a Fibonacci problem. Yeah. Uh, I didn't get it, buddy. Mm. So that's how actually, yeah, I understood your problem. So that's how it right? So if generally I make it a single line, but this is how it works, right? First you take for 5. Let me represent in the form of n equal 5. First you try to solve n equal 4, then solve n equal 3, then solve n equal 2. Then you understand it returns 2. Okay, it returns 2. Then once you done n minus 1, then you will solve n equal n minus 2. So left is n minus 1, right is n minus 2, right? Then this will return 1. Then this will return 3. So once you get 3, so you solve n minus 1. Let's solve n minus 2. This how the recursive will work, right? So n equal to, now you also know that this value also 2. So 3 plus 2, which becomes 5. Sorry, this becomes 5. So it means you solved n minus 1 for this one. So let's solve n minus 2, so which is n equal to 3. So n is 3 is already solved, so that you just get 3 here. So 5 plus 3, which is going to be 8. But while drawing the diagram, I just written in a single line. Your point is rather solving from 5, if I solve from 3, it will be get easy. That's what your point. For this problem, as we already solved, okay, tabulation, you feel comfortable for this problem? Mm, okay. Yeah, we thought about memorization, but I didn't get your point. From bottom, if we you reach the bottom only from the top, right? So it's not like it's not the recursion flow will start from top, right? Yeah, yeah, I got your point, but while writing the code, you'll get confused if you go this direction, right? While writing the code, brain will get confused. Okay, what is the time complexity here? Akash, tell me what is time complexity? Why order of n? Can you tell me precisely order in the form of multiplication? Okay, so why it is order of n? First thing is how many unique problems we get, how many unique problems we solve, unique problems. N is 5, right? So how many unique problems we solved? Solved means you get, you don't get, for solved ones, you will get only left, right. Okay, for example, if n equal 2000, then still you will solve 199 eight problems, right? Two base cases you ignore. It obviously you solve n minus 2 unique problems, right? In this case, if you closely see n minus 2 unique subproblems. But you can ignore this because if n is 1 lakh, it is again 1 lakh minus 2. So you can say that it is n. We go up, sorry, order of n. And each subproblem, we are trying to, each unique subproblem, we are trying to divide into two subproblems. It is 2n. So, but you can say it as order of n. Okay. And what is the space complexity? So DP, yeah, we'll go there. We are into memoization only, right? Or you will write tabulation and memory optimization for this problem. So this is for DP, and for stack frame also it is going to be how much? What is the space complexity of stack frame, Banu? How many stack? Yeah, because at any point in time, these are the stack frames gets active. So that obviously which is order of n. Okay, so let me quickly write it. Uh, I will write memoization, so you better write tabulation and memo optimization. Okay, so we need to define the state. I'm directly writing the memoization. Do you want me to write recursion? Okay. So if n less than or equal to 2, you can directly return n because for 1 it is 1, for 2 it is 2. And otherwise you can return climb states of n minus 1 plus climb states of n minus 2. Correct? This is your recursive solution, right? Yes or nobody? Correct, na? Why two lines? Huh? So what is the time complexity here? What is it? 2 power n, right? So we need to optimize it. So to optimize it, what do you do? Climb states, you need n. You also need a dp. So what is our base case? If the subproblem is not solved, dp of n is not solved, is not equal to minus 1, you can simply return dp of n. Okay. Otherwise, what you do? So dp of n is equal to climb state of n minus 1 comma dp and minus 2 comma dp. Then return dp of n. See, the same code, we'll just tweak it. That's it. So in this case, what you do, uh, yeah, so this is always be there. And you know, dp of 1, first you declare dp, integer array of n plus 1, 1 which is 1, dp of 2 which is 2, then climb state of n comma dp. You just remove this. Where is the mistake? Tell me, buddy. Where is the mistake? It is giving 0. Where is the mistake? Tell me. For n equal 3, it is giving 0. For n equal 2, it is giving valid result. What are we doing here? We are identifying that dp subproblem not solved if it is equal to minus 1, right? So what we should do? So we should fill with minus 1 initially. Otherwise, it will have 0. and that 0 will be returning to us. Or you should identify. Okay. Can you convert this into tabulation? If you want to convert this into tabulation, how do you do that? Let me do that. So ideally, actually, this is dp of n minus 1 and dp of n minus 2. If you try to be precisely, so this is how it is. And this is dp of n minus 1 and dp of n minus 2. So to be precise, this is how the code should look like. I just written in a single line. But if you want to convert this into tabulation, so can you try that, or do you want me to write it? Oh, write it. Okay, let me write it, no problem. So simple. So what you do, this will always remain same. The base case will remain same. And we also know 1 and 2. Definitely we should solve from where? 3, right? So it's going little heavy now. Okay. So index 3, because first and two problems we already know, and index less than or equal to n, index plus plus. So you know where to start because from 3 it will start, and copy this recurrence relationship here, which is equal to index minus 1, index minus 2, and finally return dp of n. So that's it. So it will solve it. And if you want, again, the same use case, right? So do we really need this DP array? Do we really need this DP array? So we are just using previous two subproblem results, right? So that what we can do, we can avoid this. We can have int s1, int s2, then temp equal to s1 plus s2. Hope you are following me. And s1 equal to s2, s2 equal temp, and finally s2. So recursive solution is the base for your DP problems. Okay, that's it. So what I would suggest, you try, okay, try these two problems, or you can try this and try n Fibonacci zeros, and yeah, tomorrow we will teach remaining three problems we will done tomorrow, so that we can go with the new pattern. That's it for today. It was a long session. Thanks for your time.